Hello student, good morning. I am Dr. K.Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing Charles' law. Now I will continue. I will tell more about the Charles' law. And actually I am discussing states of matter, gaseous state, part 1 you can tell. Now under that I have discussed Boyle's law, many other terms. Now Charles' law, last class I was discussing, now I will continue. Graphical representation of Charles' law. How will you represent Charles' law? Graphical representation. Charles' law can be represented by graph also. That is called graphical representation of Charles' law. And what is the Charles' law? Already I discussed. Pressure remaining constant, the volume of a given mass of a gas increases or decreases by 1/273 of its volume of 0 degree centigrade for every 1 degree centigrade rise or fall in temperature. Mathematically, I told you that V is directly proportional to T. V is directly proportional to T at constant pressure. Or also you can tell V1 upon T1 is equal to V2 upon T2 at constant pressure. Last class I have discussed. Now I am going to discuss graphical representation of Charles' law. For a definite mass of the gas, a plot of V versus T means Kelvin. Okay, in Kelvin, V versus T at constant pressure is a straight line passing through the origin. A plot of V versus T degree centigrade you can draw in two ways. First, V versus T in degree Kelvin, first graph, and second V versus degree centigrade means in Kelvin and degree centigrade both it can be represented in both ways. Okay, then for a definite mass of the gas, a plot of V versus T in degree Kelvin at constant pressure is a straight line passing through the origin. And other I am talking about a plot of V versus degree centigrade at constant pressure is a straight line. Both are a straight line, but here we can see differences. Cutting the temperature axis at minus 273 degree centigrade. In two diagram you can see two graphs are there. First graph in Kelvin, that is a graph A you can tell, and in degree centigrade B. Then first in degree Kelvin, that it is a straight line passing through the origin, and in B graph a plot of V versus T. T is in degree centigrade at constant pressure. This is also a straight line cutting the temperature axis at minus 273 degrees centigrade. This is the difference. One is passing through the origin and other is just cutting the temperature axis at minus 273 degrees centigrade. Okay, you can see the both diagram, both graph you can see. Now Now I am telling about other points. Pressure temperature law. How you can say pressure and temperatures are related, how pressure and temperature is related, that you can understand by a mountain's law. A mountain's, A-M-O-N, amount, T-O-N-S, a mountain's law. Okay, pressure temperature law is given by a mountain. What is this? That I am telling you. Volume remaining constant. Now this time volume will be remaining constant. In Boyle's law, pressure was constant, and in Charles' law, in Boyle's law, this temperature was constant. In Boyle's law, temperature was constant. In Charles' law, pressure was constant. Now in this pressure temperature law, in a mountain's law, volume remains constant. Correct? All three constant. First, Boyle's law, when temperature was constant. Charles' law, when pressure was constant. Now this law, a mountain's law, here volume will be constant. That is important. Then out of three, volume is constant. Then there will be what? Variation of pressure and temperature. Then volume remaining constant. The pressure of a given mass of gas increases or decreases by 1/273 of its pressure at 0 degree centigrade for every 1 degree rise or fall in temperature. It is the same as Charles' law, only that time volume of 0 degree, that where what was the volume at 0 degree, that we are considering. Here a change will be there. There will be change in temperature. This pressure change, there will be change in pressure. Then how will you compare? Then at 0 degree, pressure at 0 degree, in comparison to that, if you will increase the temperature by 1 degree or will decrease by 1 degree, that time there will be change in pressure. Okay, again I am telling you, volume remaining constant. Pressure of a given mass of a gas increases or decreases by 1/273, just like Charles' law. Their volume was decreasing or increasing in comparison to 0 degree centigrade, volume at 0 degree centigrade. But here volume is constant. The pressure of a mass of a gas increases or decreases by 1/273 of its pressure at 0 degree centigrade for every 1 degree rise or fall in temperature. Okay. Then this is here important point, difference in both law. In Charles' law, you have seen that 0 degree centigrade, what was the volume at 0 degree centigrade? In that volume there was 1/273. There was change in volume by 1/273 of its volume of 0 degree centigrade for every 1 degree rise or fall in temperature. But here volume is constant, then pressure will change with temperature. This is important. Okay, then here you can tell mathematically at T temperature, Pt, at T temperature, suppose pressure is Pt means pressure at T temperature, because with temperature also pressure will change. Then that time you can write just same way, just like Charles law, Pt is equal to P0 plus P0 divided by 273 into T. Correct? Because every degree pressure will change. Then T degree, how much pressure will change? Because in 1 degree pressure will change how much? 1 upon 273 of P0. Per degree 1 upon 273 of P0 will change. Then in T degree how much will change? Just it will multiply by T. Then this is a change. Then total pressure will be what? P0 plus P0 divided by 273 into T. Then same way now P0 you can take it out. Then in bracket you will get how much? You will get 1 plus 1 upon 273 into T. After solving, you will get 273 plus T divided by 273 and outside P0 because P0 is common. Hence, Pt is equal to P0 in bracket 273 plus T divided by 273. Then now 273 plus T you can write T, capital T you can write. Then now it became Pt is equal to P0 into T divided by 273, where T is equal to 273 plus a small t. Okay, Pt we are writing, that is a small t. Then now Pt is equal to P0 into T divided by 273. Correct? Pressure at temperature T. Then now you can also write that P is equal to, here you can see P0 is constant, 273 is constant, only T will be varying. Hence you can write P is directly proportional to T. This is actually a Mountain's law. Pressure is directly proportional to T. Just like Charles' law, V was directly proportional to T. Here P is directly proportional to T, temperature. Or you can tell P upon T, that is equal to constant. P upon T, because this is a proportional sign. If you want to convert inequality, if you want to convert this proportionality sign in equality, then you should multiply by some constant. Correct? That's why P upon T is equal to constant. This is a Mountain's law. Okay. Directly you can tell P is directly proportional to T, or P upon T is equal to constant. Or you can write, if pressure is changing, temperature is changing, then you can write P1 upon T1 is equal to P2 upon T2 at constant volume. This is a Mountain's law. Now other law I am telling you, that is the ideal gas. Other equation I am telling you, ideal gas equation. Actually already I have discussed in details. Now I am briefing it. Okay. And now what is the ideal gas equation? Then you know that ideal equation gas is derived from the use of Boyle's law and Charles' law. By using Boyle's law, Charles' law, Avogadro laws, all three, you will get ideal gas equation. And then what is the ideal gas equation? P1 V1 upon T1 is equal to P2 V2 upon T2. Or in shortcut you can tell PB upon T is equal to constant. And what is this constant? What is this constant? This constant is called R, where R is universal gas constant. Then PB upon T is equal to R. PB upon T is equal to R. Or you can tell also PB is equal to RT. This is for 1 mole of gas. This is for 1 mole of gas. You remember. Then suppose n number of moles are there. Then for n number of moles, what will be the law? Ideal gas equation? Then Pb is equal to nRT, a small n, where n is the number of moles. Pb is equal to nRT for n moles of the gas. Now next term I am discussing, that is the relationship between density and pressure of an ideal gas. Relationship between density and pressure of an ideal gas. Actually, in all, you can say, laws, on Boyle's law, on Charles' law, on Hamilton's law, on ideal gas equation, numericals are asked. All, you can say, laws are important. Okay. Then ideal gas equation, on that also many numericals are asked. Then now relationship, what I am telling, relationship between density and pressure of an ideal gas. On this relation also many numericals are asked. Hence you should remember the relationship. Then now here relationship between density and pressure of an ideal gas. If m is the mass of the gas, a small m, if a small m is the mass of the gas and capital M is its molecular mass, then what is the n? A small n. A small n, a small m is the mass of the gas, a small m, and capital M is the molecular mass. Then what is the value of n? Means number of moles. Then in the beginning I told you mass divided by molecular mass. That is the number of moles. In the beginning I told you. Okay, this also formula you keep in mind. Mass divided by molecular mass. Means a small n, number of moles is equal to a small m divided by capital M. Means the mass divided by molecular mass or molecular weight. Then now n value you are knowing. Then in the gas equation you put the value of this n. In the place of n you write a small m divided by capital M. This is the n, a small n. Then in Pb is equal to nRT, you have written the value of n. N is equal to a small m divided by capital M. Then now it became Pb is equal to m divided by capital M RT. Then after that you have to not do anything, just you have to just rearrange. Just then Pb is equal to m upon capital M RT. Then what is the P? Easily you can write Pb is equal to m upon capital M RT. Then what is the P? Just divide right things, right terms you divide by B, capital B. Then now there B is in down and a small m is up. Then m upon m, m upon B. M upon B is the density. Correct? Capital M is as it is. Capital M is as it is. A small m divided by B. From the left side, B you have brought right side. It is the down. Then m upon B means mass by volume. That is the density, a small d. Hence P is equal to, pressure is equal to D into RT by M. This is the relation. P means pressure is equal to D, density, into RT divided by M. Quickly you have derived from the ideal gas equation. Then pressure and density is related. P is equal to a small d means density RT by M, where D is equal to M upon V. That is the density of the gases. Thus, density of the gas is directly proportional to its pressure at constant temperature. Okay, because R, T and M for any particular gas, R value is fixed, T value is fixed, temperature at a particular temperature, molecular weight of the gas will be fixed. hence D is variable. Then RT upon M, that's just like a constant value. Then P is directly proportional to density D. Okay, thus density of the gas is directly proportional to its pressure at constant temperature. You can, if temperature you are keeping it constant, if temperature is constant, then R is fixed. R is fixed value, M is also fixed. Then P is, then R by M value is constant, and T is also constant at a particular temperature. At constant temperature, P is directly proportional to D, because R and M both are constant. That's why R upon M will be constant, and temperature is already constant at a constant temperature. Then P is directly proportional to D. This relation you also remember, because while solving the numericals, this will be used up. Okay. Now next things I am going to discuss, that is the standard temperature and pressure, STP. What you are telling, STP. So many students will sometimes while solving numericals will get confused. You should understand very clearly what is the standard temperature and pressure, STP. Actually earlier it was also called NTP, normal temperature and pressure. Then what are the condition? What are the condition of STP or NTP? Then pressure should be 1 atm, first condition. Temperature should be 0 degree centigrade, or in term of Kelvin 273 K. Correct? 273 K, that is the 0 degree centigrade. This is the condition. For a standard temperature is 1 atm, P is equal to 1 atm, and pressure is equal to 273 K, or in term of 0 degree centigrade you can tell. T is equal to 0 degree centigrade or 273 K. This is called condition. These are condition of standard temperature and pressure. Also normal temperature and pressure. Now nature of the gas constant R. Now I am going to tell about the nature of the gas constant R. What is the value of R? You should know here, or you should understand what is actually R value. Gas constant. What is the gas constant R? You should understand. Then because gas, ideal gas equation you are knowing. Correct? Ideal gas equation you are knowing. PV is equal to RT for 1 mole, and for n mole PV is equal to nRT. Then from this PV is equal to nRT, you can get the expression for R. Then what will be the R? PV divided by NT. PV divided by NT, that is equal to R, capital R, gas constant, also called universal gas constant. Then now PV divided by NT, and P is pressure. P is pressure. Then and V is the volume. N is the number of moles. Then pressure, how will you write? Then pressure is written like force divided by area. Don't forget. Always remember all the things. Okay, if you are studying chemistry, physical chemistry or physics, then you must remember pressure or force relation. What is the pressure? What is the you can say force? All things you should understand. Then pressure is equal to force per unit area. Per unit area, what is the force? That is called pressure. Okay. Then in the place of pressure, you can write force divided by area into volume, PV. Then you have written the value of P, that is a force divided by area. Down is NT upon NT. N is the moles and T is the degree temperature, that is you can write in Kelvin, degree Kelvin. Then this is the starting point, how you will write the unit of R. Only this way you can write. Force unit, you know, force divided by area, correct? Into volume divided by moles into degree, degree Kelvin, degrees Kelvin. Then now you got the unit. Then now here again you have to, for area you can write, length square you can write. In the place of area you can write length square, dimension. Then now for pressure you can write force divided by length square, L, length square. And volume, how will you write dimension? Then L into L means L power 3, length power 3, correct? Then pressure and volume dimension you have written, divided by moles into degree Kelvin. Then this moles and degree you write as it is. Then what you got now? Here force, pressure was force divided by area was L square, into volume was VQ, LQ. Then L square will cancel, only one L will remain, means force into length, only one length will remain. Length square cancelled, because VQ, it was length Q was there. The length square cancelled, only one L is remaining. Then force into length is upside, or down is moles into degree. Then again you can see concept, force into length is called what? Force into length is called what? If you are applying force for suppose some distance 1 meter or 1 centimeter, then force you are applying for some time, like for some distance, like for 1 meter or 1 centimeter, it means you are doing some work. Then force into length means you are talking about work done, W. Hence now force, in the place of force into length you can write W, capital W, and down is mole into degree. As what will be the final unit of R? Then work done per degree per mole. Down was mole and into degree, then that is a per mole per degree, it is a common. And for work, write work done, then work done per degree per mole, correct? This relation you keep in mind, work done per degree per mole, that is the R. Now if you want to know the value of R, then you have to remember R you can write in several way. R is equal to, here work done value you have to write. The work done you can write in several way. Then work done you can write 0.0821 liter and atmospheric pressure. Liter atmospheric pressure, in term of liter atmospheric pressure you can write. It is actually experimental, it is calculated. R is equal to 0.0821 liter and ATM, atmospheric pressure. There are 4 terms. In unit 4 terms will come, liter and atmospheric pressure, that is for work done, and per Kelvin per mole is there. Always this last 2 term will be common. Per degree means per Kelvin per mole. This will be always common, and beginning will change, 2 term. 0.0821 liter ATM means atmospheric pressure. This is the first value of R. This also you can write 0.0821 liter atmospheric pressure, liter ATM. You can also write 82.1. For the liter, you can write centimeter cube. 1 liter means centimeter cube. Then you can write 82.1 centimeter cube. Correct? And atm was there, you write atm only. And per Kelvin per mole was as it is. Always it will be there. Then see 0.0821 liter atm. Then that you have written in centimeter cube. 10 into 10 into 10. 1 liter you can write like this, 1000. That's why you can write 82.1 centimeter cube atm per Kelvin per mole. This is the second relation, R. Third relation, actually work done you can write in joule also. Work done can be written in joule also. Okay. Then here third relation I am talking about, that is equal to 8.314 joule in the place of work done. 8.314 joule per Kelvin per mole. Correct? This is for 1 mole of gas. You remember. Then now joule you can write in arcs also or Pascal. Arc means 10 to the power 7 arcs. You can write in the place of joule. That is the fourth relation. Fifth relation, now 8 joule you can write in, you can say kilopascal decimeter cube. In the beginning I discussed the relation, first day only. Then this 8.314 joule value will be the same, 8.314. Joule, in the place of joule you can write kilopascal, PA, decimeter cube. Okay, means for joule you are writing kilopascal, PA, decimeter cube. Correct? And per Kelvin per mole will be as it is. Then now I told you how many R value. Then 0.0821 liter atmospheric per Kelvin per mole. 1. Second, 82.1 centimeter cube atm per Kelvin per mole. Third, 8.314 joule per Kelvin per mole. Correct? And fourth, 8.314 kilopascal decimeter cube per Kelvin per mole. Correct? Now, further relation value I am telling for R, that is the fifth one. 8.314, it is the same, into 10 to the power 7 arcs, already told you. Then that is a, if you include arc, then there it is the fifth relation. Joule, 1 joule is equal to 10 to the power 7 arc. All are interrelated per degree per mole. And this, now one more relation I am telling you, sixth one. Correct? That is, you should remember, that is in the place of joule, you can write 1.987. 1.987, that is equal to roughly 2 calories per degree per mole. Okay. Exact, actually 1 joule is equal to, here joule you are writing in, you can say calories, then exact is 1.987. In the place of joule 8.314, we are writing in that is equal to 1.987 exactly. Roughly you can write 2 calories. Okay, 2 calories per degree per mole. This relation is also very, very useful. R is equal to 2 calories per degree per mole, or exact way 1.987 per degree per mole. Correct? Then this I have discussed you. Next class again I will continue. Now I am stopping only here. Thank you.